Today is our first lesson on organic chemistry. Organic chemistry implies that it comes from nature, but actually in chemistry, organic means that it's based around the atom carbon. And there is a whole range of organic chemicals that you're going to learn about over the next 5 or 6, it's going to be 5 or 6 weeks. Okay? The first one we're going to learn about is alkanes. And the reason that we learn about alkanes first is that it helps us learn a lot of basic organic chemistry that can be applied to the other, what we call functional groups. Alkanes actually don't have a functional group. They're pretty boring. They've got carbon-carbon single bonds, and all those carbons are bound to hydrogens. So we say that they don't have a functional group. But if we were to say what is the functional group of an alkane, it's the carbon-carbon single bond, which is common to most organic compounds. The one I've drawn here is the one that I asked you to make, which was C5H12. And a lot of you see that it doesn't look like what we've got on the board. It looks like that. It's a bit jaggedy, a W or an M. So it's showing that the bonds actually have an angle, which we learnt about in one of our previous topics. However, it's represented this way on a board or on a bit of paper because it shows us all of the bonding and the type of bonds that are present inside it. If I was to write out the first few of the alkanes, then we'd start seeing a bit of a pattern, and that's what I'm going to do now for you. The first one with one carbon is CH4. Carbon with 4 hydrogens bound to it. Carbons make 4 covalent bonds, hydrogens make 1. So that's why there's 1 on each of them. Then if I was to have 2 carbons, I'd have C2H6. So that would look like this. Where one of those hydrogens is being replaced for a carbon-carbon bond, and then I've filled in the gaps with hydrogens, and so on. C3 has 8 hydrogens, and so on. I start seeing a bit of a pattern here. So this is where maths is quite useful for us. We can create a thing called a general formula. If I know the number of carbons, I can predict the number of hydrogens. So where N is my number of carbons, and this 2n plus 2 is my little formula, then I can find out the number of hydrogens. So if I had 12 carbons, I know automatically there'd be 2 times 12 is 24, plus 2, 26 hydrogen atoms. So I can make predictions. So that's the first thing, and we're going to find that every functional group has a general formula. Why is this useful? Well, when we're identifying unknowns, we're often given the molecular formula. So we can predict which functional groups it could be. So you can narrow it down to 2 or 3 possible types of organic compound by looking at the general formula. So these things in green are called a general formula. What we also notice with alkanes is they only have non-polar bonds. They also have a total absence of lone pairs of electrons. Therefore, going back to our structure and bonding topic, we could infer that they are non-polar compounds. And we're exactly right with that. These are non-polar. So that means they don't dissolve in water at all. They have very low melting and boiling points for their size, so for their molar mass. As we get bigger though, as the carbon chains get bigger, so too does the melting and boiling point. And the reason for that is, as you get a larger electron cloud around a molecule, the chance of it having what's called a temporary dipole, so just one that happens by pure chance, by the electrons not being distributed evenly, the chance of a temporary dipole increases. So you get more van der Waals forces, that was the term I think we used last time, or intermolecular forces. You get more intermolecular forces between the molecules when they're bigger. Okay, and that's all you need to know is bigger molecules have bigger electron clouds, so they have a higher melting and boiling point because they have more intermolecular forces. They're not stronger, there's more of them, okay, because they're just temporary dipoles, so they're very weak. As well as that, once you get to a certain size, they actually start getting tangled up a bit like spaghetti. So those forces create it to sort of tangle up like spaghetti. So that also helps lift the melting and boiling point. It's harder to pull them apart. Okay, so that was one of the things I wanted to cover with the trends. 1, Because they're non-polar, they are insoluble in water. Because they're non-polar, they have very low melting and boiling points for their size. As they get bigger, so as the carbon chain gets bigger, melting and boiling point increase because of the increase in the number of intermolecular forces between the molecules. Okay, so that gives you a quick overview of alkanes. Pretty boring things. They do some pretty cool experiments though. We'll do that next lesson. Okay, the next thing that we have got to look at is how I name these things. So how do I actually name them? And the fancy word I'm going to use is nomenclature, which sounds pretty naff to me, but it means naming, alright? So I'm going to put it here. And I'm actually going to go beyond the first three. I'm going to write the formula up to 6, because that's what you sort of need to know off by heart. And you're going to see again a bit of a trend that you can use in other aspects of organic chemistry. So C4 is going to be how many hydrogens? 10, well done, times 2 plus 2. C5H12 we've got here, so C6H14. Brilliant. Okay. So, naming them. When we've got something that's got the general formula of an alkane, then it ends in ANE, just like alkane does. So it ends in ANE. So I've looked at my general formula, and I've gone, oh, that's the general formula of an alkane. This must end in ane. Alright, so pretty straightforward so far. Trust me, they get harder. But in alkanes, they don't. Then I look at how many carbons I've got. Now these two are actually really easy, because they're just based around the geometrical shapes. If a geometrical shape has got 5 sides, what do we call it? Pentagon. So this is called pentane. Pentane. And this one, therefore, is probably called hexane. Fantastic. Now that leads me to something else. There is a hexane which has got a different formula. C6H12. And the reason for that is it's cyclic. And I'm going to do just the carbon-carbon bonds. So each of these have got 2 hydrogens coming off them. So, sorry, I'm not going to show the hydrogens here. You would be expected to in an exam, by the way. Sorry to tell you that. So each of those apices or corners is a carbon. So there's 6 of them. And 2, 4, 6, 8, 10, 12 hydrogens. Because it's not the same as that, we've got to give it a different name. So we call it cyclohexane. Cyclo because it's in a circle. Okay? So I just wanted to show you that one quickly as well. And by the way, all the cyclics have got a slightly different general formula. You don't do the +2. Okay. Right, the first 4. These are a little bit harder. The first one is meth. All right, methane. Anything in organic chemistry which has got 1 carbon starts with METH, meth or meth. If it's a side chain, which I'll show you in a moment, then we call it a methyl group. If it's CH4, it's methane. If it was an alcohol with 1 carbon, it'd be called methanol. If it was an organic acid with 1 carbon, it'd be called methanoic acid, and so on. So anything with 1 carbon in it starts with METH. When we go to 2 carbons, we just drop the M off it. So it's ethane, ethanol, ethanoic acid, and so on. 3 is prop, so propane. So now we're into ones that we often use as fuels and so on. So propane, and then our last one here is butane. Again, another one that's commonly used as an everyday fuel. I find that quite hard to remember, and I used to make a mistake all the time as a student. I used to get prop and bute back to front all the time. Luckily, I have a really interesting craving, which is I really like peanut butter. It's my default go-to food. So I made a little mnemonic for myself that I'm going to share with you. And that is, it's a craving, so I must eat peanut butter. So that was my way to remember, because I used to always make that mistake. I used to get meth and eth back to front, prop and bute back to front, and therefore get nothing for it. I'd name things wrong. Alright, so remember it how you will, but there's a wee mnemonic if you want it. Must eat peanut butter, and then it's just the shapes. So must eat peanut butter to get into shape. There we go. Works for me. Kinda. Rightio. Now, all of these are just what we call straight chain. Before we started this video, I asked you to make as many C5H12s as you could, and we were able to find 3 of them. These are called isomers, and thank you to those of you who shared your isomers with me. The first one we got was this one here, which is the one shown here. This is what we call straight chained. The 5 carbons are just in a row. So it's called pentane, because it's got 5 carbons in a row. So I can name that one pentane. However, luckily, we were able to see there were other ways to arrange these carbons to make it look a little bit different. And this one here, whoops, which I've broken, and shall now fix, is just a bit different. We can see that there's 4 carbons in a row here, with 1 sticking up the top. So I'm going to draw it on the board because it's a bit hard to see like that. But I had 4 carbons in a row, and then on the second one, there was a carbon sticking up off it. That carbon had 3 hydrogens on it, so I'm just going to call it CH3. And these ones all had hydrogens coming off them. Just do a quick count and make sure we've only got 12 hydrogens. Otherwise, we haven't got what's called an isomer of pentane. 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 3 is 12. Brilliant. Now, the longest carbon chain in this is here, or you could argue that it's here. They both have 4 carbons in them. Okay? So, 4 must eat peanut butter, bute. So it's actually a butane. So I write down the word butane. However, it's also got this 1 carbon side chain. So we call it methyl butane. So the YL ending means that it's a branched chain. So it comes off the main trunk, as it were, of carbons. So we've got methyl butane. Now, in some organic chemicals, the side chains can be on more than one, they can be on different carbons. So sometimes you have to put a number in front of it to say where it's on, which carbon it's on. It's not true for this one, but still I'll show you how we do it. We number the carbons of our longest chain, 1, 2, 3, and 4. And we number them both ways. 1, 2, 3, 4, 1, 2, 3, 4. If I was to put a number on this to say where the methyl group is, I have to use one of those numbers. Well, this carbon's got the number 2 or the number 3 on it. I always choose the lower number, the lowest number that I can. So in this case, it's 2 or 3, those are my options. So it would be 2-methyl. I don't need to number this because if I moved it, look, it moves back onto the number 2 carbon, doesn't it? If I move that from there to there, by the way, if I moved it onto this one, it just becomes pentane again. Okay? So this one doesn't need a number because there's only one place to put it. When I give you your next task about C6H14, you're going to see that you're going to have to start numbering where the methyl groups go. It's a little bit trickier. And if there was more than one methyl group, I call it di for 2, dimethyl. And that's the one we're going to do next. Thank you to whomever gave me this one here. It looks kind of complicated and funky and all over the show. Its longest carbon chain is actually 3 carbons here. Okay? So 3 carbons through the middle, with a methyl group on the top and a methyl group on the bottom. I've kind of run out of space to draw it there, so I'll just put that here for now. And I'm going to summarise it a bit. So I'm sorry, I haven't shown every carbon-hydrogen bond there just for speed. But again, I can look at, here's my longest carbon chain, here's my longest carbon chain, here's my longest carbon. It doesn't matter. I can choose any combination as long as I'm not backing up on myself for my longest carbon chain. For simplicity, I'm going to say that that's my longest carbon chain there. Okay? Which means I should number it. Because there's things coming off it. Well, actually, I can't move those two methyl groups, so naming it's going to be quite easy. My longest carbon chain is 3. So which alkane has it got as its central part? Propane. Fantastic. So it's something or rather propane. How many carbons on each side chain? So how many carbons on this side chain? 1, so it's a methyl. How many on this one? 1, so it's a methyl. So if they're both the same, then I only have to write it once. I don't have to write methyl, methyl. But I need to say that there's 2 of them. So I say dimethyl. Dimethyl propane. As I inferred just then, your next task is to do the same sort of thing, make the isomers, and name the isomers for C6H12. There's going to be more than 3. So if you don't get at least 3, then you're missing some.